Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Design and Code of UNIX Who Utility. Before I start, let me take this opportunity to thank Bruce Moley, whose book Understanding Linux Programming has changed the way as to how I teach system programming today. The agenda of today's session is: first of all, we will quickly touch upon the concept of configuration files in Unix-based operating systems. We will see different categories of these system files and we will understand their importance in correct execution of different programs and the operating system itself. Then we will see what does who do and how does who do it. Then we will start coding some basic versions of the who command. Finally, I will talk the concept of buffering, and then we will see how we can incorporate this buffering in our who program. Well, we all know that every Unix-based operating system is actually a package comprising of the kernel itself, some startup scripts, some critical support softwares, and configuration files. The behavior of operating system kernel and almost every program that you install on it can be customized to user preferences or needs by modifying its configuration file. Moreover, in Linux programs, most of them save their data in text files in different formats so that they can be used later. And some of these files we have discussed in our previous session of Design and Code of LS Utility as well. Let us move ahead and see a brief list of these configuration files. Excuse me. First of all, let's talk about the user configuration files. These configurations are specific to every user and he or she can set these configurations as per his or her need. The .bash rc, which is read every time when a user logs in. You can write different environment variable values and aliases over here. .bash history contains history of commands executed by a user, and by default I think last 2000 commands are saved in this file. .bash_logout. This script file runs by bash whenever a user logs out from the login shell. And this .vimrc, this is used to configure the Vim editor on per user basis. All these configuration files are there in user's home directory. Let me show you an example of this before going ahead. Okay, let me cat from the home directory the file vimrc. Okay, so right now you can see there are certain values which I have set over here. For example, the tab stop value to 3, so that whenever I press tab it should move just 3 spaces ahead. Set number on means whenever I will open a file in Vim, I will see the numbering of each line over here, and the syntax on means that the syntax should be on. Anyway, let's fall back. Similarly, if a system admin wants to configure the Vim editor, he or she can make changes in the /vim vimrc file, which is located in the /etc directory. And the settings made in this global file will apply to all users, while the setting made in this file applies to that specific user only. Excuse me. Well, then we have various system administration files. We have talked about these files before as well. This file contains 7 colon delimited fields, 1 line for each user account. This contains 9 colon delimited fields for each user's password and the optional aging information. This group file contains 4 colon delimited fields, 1 line for each group that exists on the system. And this gshadow file contains passwords for every group. Then we have a lot of files for configuration the kernel. Most of the configuration files related to Linux kernel are there in the proc directory, which you all know that is created on the fly and is said to be a window into the running Linux kernel. I've discussed these files in detail in my operating system with Linux course lecture number I think 12. For example, this file proc version, this contains a string containing information about the OS type, the release, and the version. The uname command usually gets the information from this file. The proc devices file contains a list of major numbers of character and block special files. Proc CPU info, this file contains information about the CPU like the vendor, family, model, cache size, code, and so on. Then we have proc file systems. This file basically contains a list of all the supported file systems. This proc sys kernel directory actually contains range of different kernel parameters. For example, the PID max contains the maximum number of processes that are supported on this kernel. Then this proc sys fs directory, this contains kernel variables related to file system. For example, file underscore max variable contains system wide limit for open files. Then there are the other categories, the network configuration files. We'll talk about these in length in our network module. Anyway, right now remember at C network interfaces, this file contains the TCP IP configuration parameters for all the network interfaces available in the system. It includes information like IP address of that interface, broadcast address, subnet mask, and the IP of the gateway. Well, in case if there is a DHCP server available, you just mention a DHCP in front of that interface name. This etc host file, this contains host name and IP address mapping of all the machines on the local area network. So when you access a computer with the name, the system queries this file to get the corresponding IP. And etcresolve.conf is the file that contains the IP addresses of the DNS server, so that you can access the World Wide Web machines on the World Wide Web with the names instead of the IPs. Similarly, etc services file contains list of services and the port numbers on which they run. etc protocols contains list of protocols and their numbers, which you normally see in the protocol field of an IP address. Then we have some files mentioned. I have mentioned them in the miscellaneous head. etc tab and etc m tab. These are the two files that are related to the files. For example, f tab contains information about the file systems that this system can mount. This m tab contains information about the currently mounted file systems. etc local time, this is basically a soft link to a specific file in the zone information directory, USR share zone info, which contains files that store information about different time zones. Similarly, USR share locale, this directory contains files that store information about different zones. I have talked about time in my operating system video session. You can see that if you are interested in. Oh, well, in this head I have mentioned different program specific configuration files. For example, etc ssh sssd underscore config, this store configuration information for the secure shell daemon. etc apache2.conf, this is the main configuration file of Apache web server. Bind named.conf, this is the main configuration file of bind9 DNS server. And this etc vimrc, I have talked about it. This contains system wide configuration for Vim editor. Well, dear students, this is a very brief list of configuration files. There are thousands of others as well that exist in our system. And the path of these files are, which I have mentioned over here, are for Debian based systems like Ubuntu and Kali Linux. These paths may vary in case of Red Hat based systems like CentOS or OpenSUSE. So whenever you write a good program, other than writing its manual page, you should also try writing a configuration file as well, using which a user can configure your program to suit his or her needs or preference. Well, dear students, to read or to make changes in these configuration files, An expert Linux user or system administrator use different shell commands. Being a system programmer, we can either open these files using the open read write close system calls, or another option is we can use some existing library calls. But for both, we must have an in-depth knowledge of what we are doing, or we may corrupt the working of some of our programs, or may make the entire system unusable. Excuse me. Well, this slide shows some configuration files and the related APIs used to access and change their contents. We have used getpwuid and getgrgid to access the etc passwd and etc group files respectively in, I think, a previous session in which we designed the ls utility. Today we are going to design and code the who utility, which queries the utmp file, which queries a var run utmp file. This UTMP file stores information about all the currently logged in users, and information about each user is stored in a structure of type UTMP. You can see the members of this UTMP structure in the header file utmp.h. Well, there are different library functions that can be used to access the UTMP file entries. For example, get utent. This library function opens the UTMP file, reads first structure and return its pointer, and moves the current file offset to the next structure. This set utent is used to rewind the current file offset to the beginning of the file, and this end utent, this function closes the UTMP file. But today we will not use these library calls. Rather, we will use the open read write close paradigm and create our own functions that will do the task. So let's move ahead. Okay. Let us see what does who do. Well, the default behavior of who without any arguments or options is to display a list of currently logged in users, one on each line. And on my machine it displays 4 columns as shown below. And let me move on to the terminal and run the who command. You can see it is showing that these are the 4 users right now which who are logged in via these terminals, and these are the date time since when they are logged in, and this column shows the name or IP of the computer. Well, over here you can see Rauf has been logged in from this machine 192.168.1.100, while the rest of the 3 users Arif, Kaka, Mana, Zalad are using this local machine via TTY2, PTS3 and PTS4. Okay, so that means each line in the output represents a login session. Let me do man who. Okay, so do read this man page. Let me move to the end. And in the end you can see, well, yes, over here. There are 2 associated files. One is var run utmp and the other is var log wtmp. Well, utmp file, this one, it contains a sequence of utmp structures, each structure containing information about a currently logged in user. So we can say that this utmp file is a database of currently logged in users. On the contrary, this wtmp file contains a history of all logins. So right now the file of our interest is this utmp. That means every time a login process runs, a new entry in this file is created. Let's check this out. Clear screen. Let me do who. Right now there are 4 users who have logged in. Let me move to a new terminal over here and run a login process. Sudo login, and it will ask me for a username and password using which I want to log in. It should not take that much time. Let me log in as Arif and give the password, and you see I have logged in again. And if I fall back over here and run who again, you can see there is another entry over here which says I have just logged in. There is another user who has logged in. So I think the concept is clear to you. Let me exit. Let me move back over here and let me exit this session. Let me fall back and let me run who again. And you can see this entry is no more there over here. So the login program puts an entry in the UTMP file, while the logout or the logout program removes that entry. And this who program is actually doing what? It is reading that UTMP file and displaying the structure over here in some appropriate format. Okay, so far so good. Let us see the contents of this UTMP file. Let me clear screen. Let me do cat var run and UTMP. Okay, so the cat program cannot properly display the contents of this file. Let us see the man page of this file again. Well, it says the UTMP structures are declared in utmp.h. Fine. And if I move down, the members of this structure UTMP are shown over here. You can see them over here, and we can see them in the header file as well, as I have said before. Let me find that header file from usr include, and let me search it by name, and the name is utmp.h, and let me redirect all the errors to div null. And we have two files with the name of utmp.h, and let me do less to usr include x86 64 GNU bits, and inside that we have utmp.h. Fine. So this is the file. Do make it your habit to read the header files. Fine. Okay. So this is the structure, struct UTMP. Well, this UT underscore type this specifies the type of the login. And right now, the fields of our interest are this UT underscore line. This displays the terminal name, UT underscore user. This will contain the user login name. UT underscore host. This will be the host name for remote login only, as we have seen before as well. And the other thing we need is the time. The time is a structure again of type UT underscore TV, containing two fields, one to store seconds and the other to store the microseconds. If I further go down, well, over here you can see a macro, this one, UT underscore time, which contains the seconds field of the time structure. So we can use this UT underscore time instead. Okay, let me clear screen, move back, go to the next slide. Okay, so now I have a fair idea. I think I will be able to explain you how does who do what it do. So this slide summarizes what we have concluded from the man pages. The who program actually opens the file var run utmp. It reads a utmp structure and keeps on doing it till the end of the file. Display the required fields of the structure, then go to step 2, and finally it closes the file. Okay. And this is a portion of the utmp structure. This is a typo. This is not stat. This is basically utmp. And we are interested in the login name, the terminal line, the login time, and the host name. These are the 4 fields of our interest. Okay, so let us write down the first version of who. To save time, I have already written one, the basic version of who. Okay, so let us review the code quickly. Fine, let's see the main function first. The main function is opening the var run UTMP file in read-only mode. Then it is entering a while loop, and inside that while loop it is making the read system call, reading from that file and placing a record one at a time. Rec is a UTMP structure, a pointer to UTMP structure. So after this successful read call, this will be populated, and I will continue till the time I'm receiving a complete record from this file. And then I will call the show info function, and I will pass this UTMP structure pointer to that show info function, which will display that. And once this loop finishes, I will close the file and I will exit the main function. Let's see the show info function as well. Okay, so I'm just displaying the host name, the terminal, the time, and the username, the line, the time, and the host name. And well, this is a format string, and this minus sign specifies that I want to do left alignment. This 10 specifies the field width, and this 10 after this period actually specifies the maximum number of characters that I want to be printed from this string. This is just for the formatting purpose, and that is it. So let me quit this. Let me do gcc who version 0.c, and let me run ./a.out. Great. Let me compare it with who. Well, our basic version is working fine, but there are some wrinkles that we need to iron as usual. First wrinkle I want to iron is the time. Our program is giving the time in seconds, which are the number of seconds passed since UNIX epoch, while the actual who is displaying the date and time in a proper string. We have done it in our previous session as well, in which we code the ls utility, and we use the time and the ctime function to handle this. Let me show you the main page of time. This is from chapter 1, and I want from chapter 2. So it returns the number of seconds since UNIX epoch, and if I do ctime, well, this ctime function receives the number of seconds and returns a string that contains date time string appropriate to the number of seconds which are passed to ctime. Okay, so let me copy this who version 0 to who version 1.c. Let me open this who version 1.c, make changes in it. Actually, what I'm going to do is I'm going to add time feature. Okay, so what I need to do, I need to display the time in an appropriate format. So over here, what I need to do is, before displaying time, I need to convert it to an appropriate string. So let me do what? Let me long time is equal to, let me place this value ut underscore time in this time variable, and then let me call ctime on it and pass this number of seconds to ctime, and it will return a string, and I need to display that string over here. Okay, so over here I just need to display that string what? DTG, yes, and over here I just need to do ns now. I think this will fine. I have just made these 3 changes in the previous version so that the time is converted to an appropriate string. Let me do gcc who version 1.c. Oops, it says I have to add a header file for ctime, and the header file is time.h who version 1.c, and let me add hash include time.h, save and exit, compile again, success, fine. So now the string is there, but we have some formatting issues. This is a long string, so I need just this, probably the date and this portion. Let me handle this as well. Vim who version 1.c. So what we need to do over here, let me say that the field width is 10, should be left justified, and let me just display 10 characters from this. Let's see. Who version 1.c. Let me run it. Great. So it is working fine now. Although our a.out is showing Thursday, January 11, just this portion, while it should have displayed the time as well, you can always manipulate with that so that let me do that for you. Vim Hoovy 1.c and let me say the field width is 15, and let me say that I should display 12 characters from this, and let me say that the starting position of the string should be not DTG, rather DTG plus 4, so that the initial month should not be displayed. Let's check this out. Who version 1.c /a out, and now you can see that the day is not there. We are starting from the month and things are working fine. That's great. Okay. Next wrinkle. Now our program is showing 1, 2, 3, 4, 5, 6, 7 entries, while this program is just showing 1, 2, 3, 4 entries. What I want is that these two entries should not be there. The additional entries of reboot and run level. So this means that the var run utmp file seems to have some records that that does not actually represents the users, the actual users. So what to do? Let's try to find out the solution in the header file. usr include x86 bits utmp.h. Okay, I think we need to check out the ut_type field, if I'm not wrong. Yes. Well, this field ut_type, this shows you the type of the login. This is an integer value which shows what type of login is this. Let us move down and see the details of this. If it is there, it should be. Yes, it is here. So values for the ut_type field of a struct utmp, please see this. It can have these values which are shown in front of you, and I think this is what we need. So it appears 7 is our lucky number. So if the UT type contains 7, that shows a user process. So we need to show only those records from the UTMP file for which this ut_type field contains 7. So let's add this feature to our program hoov1.c. Let me copy it to hoov2.c. And let me open hoov2.c in Vim. Okay. So this is suv2.c. Let me move down to once again the show info function, and before showing I just need to ensure that this is a record in which the ut_type field contains 7. Only then these lines should be printed. So what I need to write is just a basic if that checks out if the record is the ut_type field of this struct contains, rather it does not contain 7. In that case I should return. So once the main function will call the show info function will first check out whether I need to display this record or not. If not, it will fall back, otherwise it will display. I think it should work. Let me do gcc who version 2.c ./a.out. Let me clear screen. Let me do who. And well, now you see it is working pretty fine. Great. We have almost done with a basic version of who. Let's move ahead. We are done with version 0. We are done with version 1. We are done with version 2 as well. Okay, so next thing I want to do is I just want to touch upon the concept of buffering. Well, we all know that system calls are expensive as there is a mod switch involved. That is, since the code of every system call resides inside the kernel, so whenever a user process makes a system call, the control shifts from the user space to the kernel space, executes the code of the system call over there, and then falls back to the user space. And this is what is shown in this diagram over here. There is a user who has run a process P1, and if this P1 is making a system call, it goes over here and then it falls back over here. So there is a mod switch for every system call. Let's suppose that there is a text file of 1000 bytes and a process reads that file one character at a time and then writes that file to std out again one character at a time. So there will be a total of 2000 mod switches. On the contrary, if we read or write 100 bytes at a time, there will be just 10 mod switches, or maybe 20, I think, if we do 10 for read and 10 for write. So performance will be improved. It will be improved to a great time as going to the kernel mode and coming back from the kernel mode also needs some time, and we have seen this in probably our first or second session as well. Let me just do a proof of concept. Let me move on to the terminal and let me create a big file of let's suppose 10 megabytes using the dd command. We have used this command as well. The input file is div0, which contains an infinite trail of 0. The output file is, let me name it zeros.txt. The count is 10 and the block size that I want to write is 1048576. That is 2 raised to the power 20. So what this will do is it will read this file, this much block size, this much time, and write in this file. So okay, count, sorry for the typo, count, count. So what it will do is it will create a file of 10 MB which will contain just zeros with the name of 0.txt. So we have a file of about 10 MB. Let me do LH, human readable format. Okay. If we write a program that reads this file character by character and copies them to another file, so let's see. we have a copy program for this. Let me do time cp0.txt to another file. Let me name it copy. And you see it has just taken 0.039 seconds to copy a 10 MB file, the actual cp command. Let me write my own cp command. Rather, I think I have one, my copy.c. Okay, so let me quickly go through the code. Probably you have written this before in some previous session. This is a macro, buff size is 1. We receives 2 command line arguments and both are file names. This is the source file and this is the destination file, the second command line argument. I'm opening the first argument in read-only mode and I'm assuming that this file exists. I'm not doing any error handling to keep the code simple. And this is the second file and I'm opening this file in read-write mode. I'm creating this file, truncating it, and I'm creating a buffer size of size 1 and I am entering in this loop. And what this loop is doing is it is reading from the source file character by character and it is writing to the destination file character by character. So naturally read call will return 1 because it will read 1 character at a time because buff size contains 1, and it will write to the destination file character by character. And once read returns 0, that means we have reached the end of file, so it will close. I hope this code is clear. Let me do gcc my copy.c and let me run again cp the file zeros.txt to a file copy, and let me time this command which will tell me how much time I'm taking, and let me now run the same on with this. And you see this program is taking much more time than the actual cp command, because this time I'm calling the read and the write system call with 1 character, so it is taking almost 9.178 seconds. Let me change the buffer size and let me make the buffer size to, let's suppose, 10. I hope this will reduce the number of system calls to a great lot. Let me do time./a.out zeros.txt. Let me copy it, and you see this time it has reduced to 1.096 seconds. Let me change it again. Let me make the buffer size to 1K 1024. Let me do gcc and let me run it again. Great. So you have seen that if I am reading character by character, my program is taking over 9 seconds. If I'm reading 10 characters at a time, it is just taking 1 second and 96 milliseconds. And if I'm reading 1024 bytes at a time, so it is taking just 78 milliseconds. Let us move back to the slides. So now we have seen the importance of buffering, and the idea is read data in big chunks into the region in the process address space and then processes that data as you need them. So this process should not read 1 character at a time. It should read, let's suppose, 1K characters at a time, and then it should process those 1K characters so that the number of mod switches should be minimized. Great. Now a $100 question is, if the buffering is so good over here, does the kernel do the buffering as well? Well, yes, it do. Whenever you tell the kernel to read even a single byte from a file on disk, the kernel does not read 1 character. It reads some disk blocks from hard disk into the kernel buffer and gives the process as per the request. And if the process calls a request for more characters, later the operating system kernel just copies from the kernel space to the process space. And when the kernel buffer goes empty, it suspends the process and adds the requested disk block to its shopping list. and continue with the execution of some other processes over here. And sometimes later it goes to the disk and get all the data that is requested by many processes, and then it restarts servicing those processes. So to conclude, let me say that a read call copies data from kernel buffer into some user space buffer, and a write call copies data from a user space buffer into the kernel space buffer. And transferring data between the kernel buffer and the disk buffer is different from read write calls. Okay, so that means that we have certain consequences of kernel buffering. The advantages are fast disk I/O and optimized disk writes, and the downfall is need to write buffers to disk before shutdown. So let's suppose that a process has told the kernel, requested the kernel to write some data on the file on disk, and the data is still residing inside the kernel space in the kernel buffer, and the operating system shuts down immediately. This data will not be written in the file, which may get corrupted. Okay, now you have the idea of buffering. This part is to be done as assignment. You need to add buffering facility to this who program. I will like you to create some functions that perform the task like the get UTENT function. You need to create a library with some appropriate header files, write the main pages for your library calls. Do see if you can add a configuration file that can be configured by the user and read by the who utility that you have written. Make a test driver of it, check it out. Finally, I would like you to make a package of this utility using the CMake and distribute it to the open source community. Well, I'm sure if it is good, maybe someday it becomes part of some Linux distribution. Okay, that is all for today's session, dear students. Hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best. Happy learning and Allah Hafiz.